Okay, so good afternoon, everybody. Welcome to this session. My name is Paresh Gupta. I'm a principal engineer at Cisco, focusing on AI and networking. If you look at the title of the session, it says, why Cisco Nexus 9000 switches for AI networking. I got rid of Nexus 9000 switches from here because a lot that I'm going to talk applies to other products as well, and we are expanding the scope, right? So with that in mind, I see some of you are coming back, so thank you for coming. I hope you find something new. Of course, just like every other session, feel free to ask questions, right? The entire reason we organize this show is for you guys, right? So if you have any questions, any doubts, any topics that we did not cover today, feel free to ask later as well. I'll be here after this session, right? Now, this is the agenda. This is very similar to what I wrote down on the description. The only point that I want to convey is that this is a vast field. Like, some of you are building AI clusters, right? Then on one end, there are hyperscalers who are running thousands and thousands of GPUs in our distributed training. On the other side, we have enterprises. So we cannot cover all use cases in 90 minutes, right? So remember, this is a 1,000 series session. That means basics, foundational topics. These topics will help you regardless of what scale you build at. Okay? But as I said, any further questions you have, feel free to stand here and wait after the session and we can talk about those topics. Okay? All right, so as I said, as a principal engineer in Cisco, I get to work with a lot of customers, and what I see is that there is a whole range of these customers. On one end, we have hyperscalers. These people have thousands, even tens, or even hundreds of thousands of GPUs. They're talking about building AI clusters of millions of GPUs. On the other side, we have enterprises who have maybe tens or even maybe thousands of GPUs. And in between, there are whole segment. There are neoclouds. Neoclouds, we are using this term for those organizations who are building purposefully offered GPU as a service. And then we also have some sovereign clouds that are coming up. These are government-based initiatives that are focused on keeping data internal to their geographical boundaries, right? Now, there are some significant differences to them. So not just about the number of GPUs, but also about what are the use cases. So hyperscalers are a lot focusing on doing foundational training. If you have heard about models like Llama or GPT-3 various version, or GPT-4 and the 5.1 as well, all these are like training use cases. But then a lot of enterprises may take these foundational models, they fine-tune the models on their own data as per their own use case, and then provide value to the end user. So the value providing to the end user comes from inferencing of a model. When you open ChatGPT and ask a question to ChatGPT, that's inference. That's when it becomes useful to you and it becomes useful to me, right? So difference is that not everybody is doing a foundational training of the models, but almost everybody who has AI cluster or planning to build an AI cluster will be doing fine-tuning, inferencing, and related areas. The other thing is there are concepts like scale up. So what is scale up? In a very short way, all the GPUs that are part of the same high bandwidth domains. In other terms, all these GPUs that are part of the same physical enclosure, like within a server, that's scale up. Scale out, you take multiple of these systems and connect them with a network. That becomes scale out. And then scale across is really for hyperscalers because they have so many GPUs that they don't have enough power at one location to connect all these GPUs. So they have different locations and probably 100 kilometers away, maybe in different states, and then they are trying to connect these systems. That's scale across. I don't see that happening. I don't see scale across happening with enterprises, right? So in enterprises, most customers are still scale up and scale out. Other difference is I see significant amount of research and development resources being spent from hyperscalers. That also means they are writing their own software libraries. right? And that's very important because a lot of times I get to hear from customers, hey, I read this paper, I read that news, let's say one hyperscaler is doing something, why can I do the same? The reason is they wrote their own stack. Are you ready to write your own stack? So be aware of that. Ask those questions that, is this the right solution, or would you rather depend on a vendor to provide you fully validated software and you just use it? Just like the way most enterprises have been using till now. But having said that, the opportunities are very different because there are only a few hyperscalers in the world, but then there are thousands of enterprises. And look, why I'm telling you all this, because, as I said, because the environments are different, the challenges are different, and therefore solutions must be different. So yes, we take some partial learnings from what's happening across the industry, but that does not mean anything or any kind of network designs or any kind of software optimizations that you get to hear from hyperscalers that may or may not directly apply to you. Right? So with that background, when you ask questions that why is it done this way, a lot of times answer will depend on these differences, because what's the problem you're trying to solve and what your environment allows, right? So answer will come out from the business perspective, which is kind of summarized here. Okay? Now, we'll keep on going further, one level at a time. But before that, let's start with the very basics, right? So what exactly is an AI cluster? Essentially, when we talk about AI cluster, we are talking about massive computational power, right? That's any accelerator. Another term for that, because of NVIDIA, is GPU, graphics processing unit. These GPUs are within servers, but the kind of computational capacity we need in today's world, a single server is not enough. So we have many such servers. Now, what exactly server looks like? Something like this, right? So until like last year before, we had these 8RU or 10RU servers. There are different branding for it. NVIDIA calls it as NVIDIA HGX architecture. Each server has 8 GPUs. On the left, you see Cisco's implementation of that HGX architecture called UCS 885A. If you take a look on the network connectivity and network ports of that server, there are 8 400 gig ports on it, just for GPU to GPU communication, also called as backend network. And then there are some 2 or maybe 4 ports running at 200 gig or even 400 gig for front-end or storage connectivity. Now, that was last year. If you look at today's world, most of the deployment are focused on NVIDIA's B200 or even B300 GPUs using the ConnectX 8 Super NIC. ConnectX 8 is an 800 gig NIC, and there are 8 800 gig interfaces per server. That's 64 gigabits per second, 6,400 gigabits per second of capacity just for GPU to GPU communication, and then we have 400 gig connectivity on front end too, right? I don't think outside the scope of AI infrastructure, this kind of connectivity exists on any other servers, or maybe HPC environments too, high performance computing environment too. But this is the connectivity, and be aware, all this connectivity is used. All these ports are saturated. I'll explain you a bit more detail. Right? So this capacity is really used. In fact, that's the reason every 12 to 18 months, there's a new generation coming, because what we have today, we are already using that. Okay, so we have multiple such servers, and now we want to connect these servers. So what we do, we create multiple networks around them. One of them is a front-end network. This is the network we use to access these servers. Now, because these servers have GPUs, the GPUs need storage to do their computational task. So if you take a look at my Cisco Live presentations from 2 years back, I went on the stage and I said that for your best performance, I highly recommend you to have dedicated storage network, which is separate from front-end network. Guess what? I still say that. I still believe into that. It has some technical merits, but I don't see that happening anymore because the bandwidth requirement on front-end is minimal. So people are thinking, you know what? It's not the best use of investment to have dedicated networks. Let's just merge that. So over last, I would say 12 to 18 months, what I've seen most customers deployed as a converged front-end and storage networks. Now, of course, when we have storage networks, we must have storage. So typically, this is high-performance storage because GPUs are running so fast, we don't want to make them wait for data read and write to happen. So there must be high-performance storage. And there must be, or there may be, a back-end storage network as well, depending on the kind of storage platform you use. For example, VAST, if you buy a VAST platform, a VAST data platform, it has the concept of a back-end storage network. If you buy other platforms, let's say DDN, it doesn't require a back-end storage network. If you buy Weka, it doesn't require a back-end storage network. So here, this may be an optional back-end storage network. And then there may be some standard storage. Why? Because if you're taking logs, you don't need high-performance storage for that. If you're keeping your images somewhere, the ISO images, you don't really need high-performance storage for that. So, make the solution more affordable, have some standard storage there. And then for these GPUs to talk to each other, there's a dedicated inter-GPU backend network. There may be one or more than inter-GPU backend networks. We'll talk about that. And then because there are so many devices here now, to manage these devices, there must be an out-of-band management network that connects to all of them, typically via RJ45 connectors, Ethernet cables. Now, this is a typical view of an AI cluster. But remember, it's not just like an AI cluster lives by itself. On top of that, there must be a data center network layer, right? So that's where our data center fabric comes. This is something I'm assuming for those of you who have experience in maintaining data center networks, you are very familiar with what I'm talking about. And then because this is a whole organization, you would have some centralized data. This is where your raw data sits. Because if you are reading enough about AI, 90% of time is spent in preparing the data to be used by these AI applications. So this data must live somewhere. So this is where it lives, which is an organization-wide storage. Then there might be some AI apps. There might be some other services running, which are existing services. And then we have the users and the applications that are making use of these AI clusters. Right? Now, let's go through what happens when a typical request comes. How does the traffic flow looks like? So imagine a user, maybe a user is there, open up maybe an application. The application may do 10 other things. One of the things it does is provide an AI-assisted application, maybe a chat GPT. Everybody talks about chat because it's chat GPT. So let's say there's a chat app within the application that makes use of AI. That means when you open the web interface, that does not mean the request directly goes to a GPU server. No, it doesn't happen like that. It probably goes in some other app. There might be some other traffic flowing between other kind of networks in data center. Why? Because of identity service, because of role-based access control and other things. And there might be back and forth happening. And only after that, if the application decides it needs to access the AI cluster, the request will travel via the typical data center fabric and will go to the front-end network and land on a GPU host or a GPU node or a GPU server, whatever term you like to use. Now, when the request reaches the GPU node, to handle that request, it must access the data, the high-performance data. Right? It may be read or write. If, as I said, if the storage platform requires a storage backend network, there may be traffic on the backend network now. At the same time, the application may want to take some logs. So because of that, there might be traffic flowing towards the standard storage. At that time, standard storage may realize, you know what, I don't have the hot copy of this data, so I need to go back to the organization's centralized storage and bring this data back. So that may happen too. And by the way, if the job is large enough that it cannot fit within a single node, then the job would run on multiple nodes at the same time. And for this job to run in a synchronous way, there would be traffic on the inter-GPU backend network as well. And finally, when the job is done, or maybe it's time to send the tokens back to the user, there might be requests going back, which may directly go back to the user, or it may get routed via the application, right? Both options are possible depending on how things have been configured. But I hope this gives you perspective on the overall traffic flow within an AI cluster and much before the AI cluster too. And the reason I'm bringing it to you, because most of the times when we talk about AI networks, most of the times people think about GPU to GPU communication backend networks only, right? So this is the entire traffic flow. Question?
Just want to know, at what point does the tokenization happen?
The synchronization happens?
Tokenization.
At what? So the question is, at what point the tokenization happens?
Yeah.
The tokenization happen would after step 5. After step 5, when the request reaches the GPU servers, that's where tokens will be created and sent back. Now, there would be significant amount of processing involved there.
So not where you've got apps with AJAX, yeah?
May or may not be. Look, there are exceptions to all these rules. You may do some inferencing even without GPUs also, right? There's a CPU-only inference concepts too out there, very well used, right? But to understand the network perspective, we have to make some assumptions. We have to make some, common grounds, and then we move forward. But yes, I mean, you may do inferencing and tokenization even at between step 2 and 3. That's possible as well, right? And if that happens, probably a request is not even going to an AI cluster as such. Okay. Now, a quick note on terminology. I mean, it happens a lot. People who understand it, they don't get worried. People who are new, they get confused all the time. When the GPUs of different nodes talk to each other, that's called east-west traffic from the perspective of an AI cluster. That's east-west traffic between GPUs. However, we also overload this term for other purpose. When the traffic exits or leaves, so all the traffic that I've circled here on this drawing, that's called north-south traffic from the perspective of an AI cluster. However, there's other kind of traffic that is also called east-west traffic. But now the perspective is data center traffic. Remember, forever we have been saying all the traffic that's between the servers of a data center, it's east-west traffic. Only the traffic that leaves the data center is north-south traffic. That means there may be some information overload or the overloading of the term, so do not get confused. When people say east-west traffic, if it's a perspective of AI cluster, people are always only thinking of GPU to GPU communication. But if it's a typical data center network, people are also talking about, let's say, storage traffic is east-west to them. But for AI cluster, storage traffic is north-south traffic. Okay? All right, so of course, there are many challenges with all this infrastructure. I took a few that I keep on hearing the most from other customers, right? So, of course, the one part is there are so many moving parts here. So people are looking for validated designs and validation. So that's one. The other one is the simplicity. There are too many moving parts here, right? GPUs, networks, transceivers, cables, storage. So we got to simplify it. Of course, observability without knowing visibility, and this is something I'll talk about a bit more. Typically, let's say if you're running a distributed job in a network, even if one link fails, the job crashes. At that point, you want to know which link failed as soon as possible. And link failure is just one condition when the job may fail. So there might be other conditions too. So you want to know about these conditions as soon as possible, because the longer your jobs are not running, the more pressure you are under from management that, hey, why the cluster is down? So because of that reason, you must have the observability. And then there are some standard challenges with your front-end network and back-end network. Some of them are very, very classic challenges, like network delay, congestion. But then there are some very specific and new scenarios. One of them is when these GPUs talk, they send and receive traffic at line rate at the same time. Remember a few minutes earlier, I said that a B300 server has 800 gig interfaces. All of them send and receive traffic at the same time. Now, that traffic pattern is unprecedented in the networking industry. Not that we have not known about it. We have all read books, of course, but we don't see that kind of traffic pattern in production networks. But we see now with AI clusters. So because of that, there are some challenges. We'll talk about them. And of course, we have similar challenges in storage networks too. The difference in with storage, there's a lot of time in-cast problems happening. If many GPU nodes are reading the data, a lot of traffic is coming back at the same time on the same ports. Or if they're writing data, a lot of data is going back to the same storage nodes at the same time, right? So we'll look at those challenges, and then some of the solutions I'll discuss with you. All this is making sense? Again, as I said, this is a 1000 series session. We try to keep it basics, assuming there might be some folks who have not done this before. All we have done is use ChatGPT. Right? But this is an oversimplified representation of how a typical AI cluster looks like. Okay, let's go one by one. So let's talk about reference architecture. This photo is coming from now 3 weeks back from NVIDIA's GTC conference at Washington, D.C. You see a lot of faces here. Most of them are my peers or the other folks I get to work with in Cisco, except one person. That's CEO of NVIDIA. And the reason we have this photo together, because Cisco has done a partnership with NVIDIA, and we made multiple promises out of that. I will explain all these commitments that we did. One of them is writing an enterprise reference architecture with NVIDIA and Cisco. So the enterprise reference architecture is a reference architecture primarily designed for enterprise environments, essentially up to 1,000 GPUs. And this reference architecture gives you a modular unit. People also call it as a scalable unit with, let's say, 4 servers at a time. So you can buy 4 servers, add more to it. This is the kind of network you'll need. This is the kind of storage you need, and all the small little details that you need. However, there are some customers who are deploying larger clusters. So we recently wrote a cloud reference architecture. This is Cisco's cloud reference architecture that defines GPUs more than 1,000 in number. The published document explains up to 32,000, but we also have designed for 64,000 or even larger environments. And the third bullet, or the third key reference architecture, is related to the photo that you see on the right, where Jensen, CEO of NVIDIA, is signing on a switch. That's a special switch. Why? Because within the switch, the ASIC that we have used, it's NVIDIA Spectrum Ethernet ASIC. So it's NVIDIA's ASIC, but it's a Cisco switch. And we use that switch. Why? Because that switch is compliant with a program from NVIDIA. It's called NVIDIA Cloud Partner Reference Architecture. So if those of you who care about it, that's the switch to look at. If you don't care about, forget it, right? Go with the Cisco reference architecture. Now, although we are building switches with our own ASICs, which are Silicon One based, in Cisco we use the term like Silicon One, and before Silicon One we had ASIC line called CloudScale. Using those, we have written enterprise reference architectures and cloud reference architectures, and then using NVIDIA Silicon, we have the NCPRA, or the NVIDIA's Cloud Partner Reference Architecture. The point is that all these products, all these switches run a common operational model, which is using the same NXOS operating system, if you're aware of, that runs on Nexus switches today, managed by Nexus Dashboard. You can also, some of these switches also support SONiC, especially the Spectrum Silicon-based Cisco switch will support both NXOS as well as SONiC, managed by the same operation platform of Nexus Dashboard. So that means now there are solutions, regardless of where you are in that whole spectrum of GPU deployments, maybe a hyperscaler, maybe a neo cloud, maybe enterprise, we have a solution for you. And all the details are mentioned in these reference architectures. But not just with NVIDIA, of course, NVIDIA is the biggest name in the field of GPUs, but then we have validated within AMD too. Recently, we completed a validation environment that's running in Austin Lab. I went there to configure the network. For a few weeks, we ran all the benchmarks, and then we claimed the success of this validation with AMD GPUs. Last year, I did the Intel Gaudi 2 validation. You see photo on the extreme left for you. And recently, we finished the Intel Gaudi 3 validation as well. Along with GPU vendors, we are doing the same with storage vendors too. All this information is publicly available. If you don't find that, reach out to us and we'll help you out with that. And most importantly, we have an in-house benchmarking team. This team is dedicated for this purpose because Look, this is a massive investments we are talking about, right? Like, I'm sure you guys are seeing why NVIDIA has become, like, recently more than $5 trillion company. Of course, people are putting heavy amount of investments there in buying their infrastructure. So when they buy, they want to feel confident about it. They don't want to take chances. To make them feel confident, we have an in-house GPU benchmarking team, and you see some of the tests that they are running. But we have a long pipeline of customers who are coming on site in Cisco's lab environment. They are bringing their models, we are running them, and we are proving them, yes, using our infrastructure, using our networks, using our operation model, you can achieve the performance that you expect. Question?
NVIDIA could just make their own switches, right? So why have they partnered with Cisco?
Yes, so question is, NVIDIA have their own switches? So why they have their Ethernet switches too, and why they are partnering with Cisco? The reason you saw on the bottom of the slide, the common operating model, right? There's significant number of network engineers out there, right? And I'll give you some reasons going forward that it's not just like a backend network by itself. Remember, I showed you many networks out there. So customers who have front-end networks running, let's say Cisco NXOS. Now, if you tell them go have another operating system running on backend, it's a bit of a barrier to entry now, right? So both NVIDIA and Cisco realize we want to get rid of the barrier and make it simple for the end users.
Is Cisco then providing switches for hyperscalers, or they just doing their own thing, and this is more for enterprise?
This is for anybody who wants to buy. So these switches, we are not limiting by customer segment. Maybe hyperscalers, maybe neo clouds, sovereign clouds, or enterprises. Whosoever want to buy it.
Hyperscalers actually buying Cisco, or?
Yes. That's the reason I had mentioned it on the very first slide.
Yeah.
Right. Okay, so that was about validation. The next point I mentioned, the challenges that I see is about operating models. So from Cisco, we offer on a very high level. Look, you can find some exceptions here and there. On a very high level, 2 operating models. Number 1, using Nexus Dashboard, which is the on-premises manager for on-premises switches. So this is for network management. You can get your own GPU nodes, you can get your own storage, you can connect them via network, and all these different networks that I talked about can be managed, can be monitored using Nexus Dashboard. In the coming slides, in the coming minutes, I will talk about some of the features that Nexus Dashboard provides. But there are some customers who say that, you know what, I don't want to have anything running on-prem. I want to have something cloud-based that Cisco manages, but me as a user, I just want to use it. So that's where we have HyperFabric. HyperFabric is a Cisco-managed cloud controller. So Cisco manages everything about it. All you need to do is use it. But it manages switches on premises. So you have the switches in your own premises, and HyperFabric manages it. There's an extension of HyperFabric called HyperFabric for AI. What HyperFabric for AI does, it provides a prescriptive full-stack solution that includes network, servers, and storage. Storage today comes from vast data, but in future, we may extend to other offerings too, right? So if you want an easy button, if you're building it for the very first time, I would go with HyperFabric for AI. Right? But if you know what exactly you want, and probably you say, you know what, I don't want that specific piece, then sure, go with Nexus Dashboard and pick whatever you want. Right? One example, let's say if you say that, you know what, I probably don't want to use vast data. I mean, we want you to use vast data, but you may have your own reasons. If you don't want vast data, you want something else, maybe DDN, maybe Weka, maybe NetApp, maybe anybody else. Sure, you can still get all this whole stack, but then you can use Nexus Dashboard to manage that infrastructure. And you can also use HyperFabric, by the way, to manage that infrastructure. It won't be just the HyperFabric AI, because HyperFabric AI is a fully prescriptive offering. Question?
So if you go with the RISE, where does the data live, on-premise or in the cloud?
Say that again, I did.
If you go with the RISE, the data is stored where? In the cloud or on-premise?
I missed the word. What exactly in the cloud? The data?
Yeah, where is it stored?
The data of the fabric or your own data that you're using for AI? What?
Data
So your data does not go to, so the question is, where does your data live if you use Hyperfabric? So your network management information and the telemetry goes to the cloud, but this is only the switch or the network view, but your organization data stays on premises, right? So let's say if you're running an AI task on GPU servers that needs some access to the data, that data remains on premises, right? Hyperfabric is not touching the data. It's just managing the devices.
Sorry, so the only thing that gets into the cloud is the telemetry.
Yes, that's right. And the management information of the switch. Yeah? Okay, so Nexus dashboard. This is one example that I want to bring forward. I think somebody asked, question that why NVIDIA did this partnership. Here is one reason. It's not just a backend network. It's the management network that may run VXLAN. There's a data center fabric that may run VXLAN. And typically, at least today, most of the backend networks, the inter-GPU backend networks, are flat L3 routed networks that may use eBGP. There may be some other networks too in your environment. All these networks can be consistently managed by Nexus dashboard. Not just that, the API framework is same too. If your teams have already automated this, most of that can be reused. So that is the biggest reason. And you have a larger enhanced view, you can just take a look on the type of networks that are pre-built as a fabric type within Nexus dashboard, and these can be used to configure these networks with a few steps. For example, what I've selected here is an AI fabric type. In the coming minutes, I will talk about some of the fine-tuning that's needed to achieve that best performance out of the network. All these fine-tuned values are already pre-built in this template. You don't see any. Of course, you can go and edit fabric settings and change whatever you want, but all the best values we have already encoded within this AI fabric type based on our own benchmarking that we have done. Right? So this is the value that the common operating model of Nexus dashboard and NXOS, even Hyperfabric brings to the customers, and this is the big reason of this partnership.
You're selling the solution like as a Nexus as a software product or software with hardware?
This is so question is, how are we selling the solution? So it's essentially a switch. I'll show that switch in a few minutes. The switch we sell, and of course the software that runs on the switch we sell. So hardware plus software. Yeah, it's essentially a 64-port of 800 gig switch in 2RU. I have a photo coming in a few minutes. Yep. All right, so let's take the next step and talk about what kind of traffic do we see in these networks, right? So essentially, I think going back to the very basics, the very first networking book we read, we talked about TCP and Ethernet and UDP and TCP versus Ethernet and all that. It goes back to the same basics, by the way, right? With some differences, and I'll cover those differences. Most of the access to the GPU nodes happens via some kind of TCP connection. If you're doing SSH, if you're doing HTTP transfer, if you're doing FTP transfer, even if you're doing NFS for storage access, that uses TCP. So most of the time, front-end traffic is TCP. But then if there's high-performance storage, most of the high-performance environments today, they use RoCE. Now, what is RoCE, by the way? We call it as RoCE. It's essentially RDMA over converged Ethernet, and then there's a version 2 of it. So people call it as not RDMA OCE v2, rather we say RoCE version 2. That essentially it is. If you are a network engineer, all you need to worry about that this is essentially a UDP IP packet, nothing more. In fact, there's no RoCE v2 header here. If you look at TCP packet, there's a TCP header. You can clearly see there. On the right, in RoCE v2 packet format, there's no RoCE v2 header. It's just a name. It's just a name, right? Also, the backend, the GPU to GPU communication uses RoCE v2. Now, why RoCE v2? Of course, there are a lot more details to it. In very simple terms, all you need to remember is for RDMA over network transfers, there's a memory-to-memory transfer happens without involvement of the CPU. So if two GPUs are talking, one GPU can move some data from its own memory to the memory of another GPU without involving the CPU. So that improves performance significantly. And one of the ways of doing this remote direct memory access over the network is over Converged Ethernet. So that's version 2. And we can use the same technology for storage, and we can use the same technology for GPU to GPU communication. That's all you need to know. Of course, there are a lot more details to it. You can spend your own life. And there are some people who are working for 20 years on it. Right? But this is all you need to remember for this session. Now, what are some basic differences? One of the basic differences is that TCP is a connection-based protocol. It's very basics. I'm assuming, if not all, most of you. And like, if you don't remember all these things, even I don't remember all these things all the time. All you need to remember is, number one, it has a built-in congestion control mechanism. Right? So that's one. Now, UDP, by definition, does not have that. And it's by design, because if you implement a congestion control mechanism in the protocol, it becomes heavier. It becomes heavier. It doesn't deliver that performance. Right? So that's number one. How is that congestion control algorithm implemented? A basic concept of notifying the end devices by the network when the network sees congestion. So if you think about our freeway systems or highway systems, whatever name you use in your country, think about if our freeways are congested or highways are congested, if somebody informs all the people who are about to leave their homes, hey, don't start. There's significant congestion. That's what ECN is. The other mechanism is based on the round trip time, where the end devices measure and account for the round trip time of the traffic. And if the round trip time increases, it reduces its rate. And if the round trip time improves, then it sends more data. So TCP had these things mostly standardized. When RoCE was written for the very first time, there was no such provision. Later, people realized, you know what, of course, there cannot be a network without congestion management. So RoCE v2 congestion management was added later, but only the idea was written in these standards. The implementation was left to the vendors. So initially, there was a mechanism that was based on the same ECN concept. ECN stands for explicit congestion notification, where the network notifies the end device. And in last few years, a similar concept based on RTT, round trip time, has also surfaced. Right? So similar mechanisms, different implementation. The third most important factor is TCP also has a built-in retransmission if a packet is lost in the network. Right? So if you're aware of the 3 duplicate ACKs, that's what the mechanism is. TCP has that thing built in. UDP does not have it. And because of that reason, we run RoCE on a lossless network. And also, if a packet is lost, there's a significant performance degradation with RoCE, which we'll talk next, but before that, there's a question.
The question is that, as you rightly said, with TCP got window sizing and other factors to deal with what you couldn't do with UDP. With RoCE v2, I'm guessing there are additional factors for lossless Ethernet. But we do know that with TCP, you still need force and other network-based, whether it's buffer, queuing, or whatever you call it. With RoCE v2 in the AI backend network, are there still implementations of additional checks and balances on top and above what RoCE v2 can provide?
Yes. So if I repeat the question short, are there checks and balances in RoCE v2? Yes, there are many enhancements out there. I'll give you one example. TCP also has this concept of selective ACK. RoCE has that too. People enhance these things over the years, right? Look, ideas, for those of you who have been around in industry, we all see one idea comes here and like it gets copied somewhere else or leveraged somewhere else. And yes, so these ideas exist, right?
Sorry, what I meant was on the AI backend network switches, do they still have congestion management techniques like buffering and queuing in addition to what RoCE v2 as a protocol can do?
That's right, yes. So there's a whole congestion control mechanisms on the network, on the NIC. We'll discuss some of them in upcoming minutes. Yep. Okay, so quickly let's talk about how or why exactly there is a significant performance drop when the packets are lost. Before that, why exactly packets get lost on the network? Packets got lost in the network because of two reasons. Number one, bit errors. Number two, network congestion. Right? Regardless of the cause of that, if you look exactly how exactly RDMA over converged Ethernet is happening on the network, I'm taking the example of, let's say there are 4 GPUs, they're talking to each other. And they're doing 4 megabyte of memory transfer with each other. Typically, Rocky uses a packet size of 4 KB, 4 kilobytes. So that means 4 megabyte translates to 1,000 packets. So each GPU is sending 1,000 packets to the next GPU in this whole collective communication. They're all talking to each other. That's why we call it as collective communication. The way it works, this is exactly if you tap into the wire, you see this is how exactly there's a first RDMA transfer, then there's a middle RDMA transfer, there's a last RDMA transfer. Each of them carries a packet sequence number. If one of this packet is dropped, there have been multiple schemes. A couple of years earlier, there was a scheme where, hey, if one of the packets is dropped, let's just send everything. Not very efficient, as you can imagine. So people changed that, and people said that, you know what, if we drop one packet, let's just send packets since the drop packet, since the last drop packet. So if 1,500 packet is dropped in this example, then not all the packets will be resent, but all the packets after 1,500 will be sent again. Well, regardless of what you do, what's going to happen is at least, even if there's small number of RDMA operations are delayed, the whole collective communication is delayed because the collective communication is not complete until all the operations are complete. Right? So if you plot the completion time of the graph, there's a long tail of that graph, and that's why it's called as a tail latency. And because of this tail latency, the performance degradation is significant. We want to avoid that. And that's why we don't want to drop any packets in rocky environments. Now, to avoid packet loss due to network congestion, we can enable flow control on the network using priority-based flow control. This runs between two end devices. So let's say if there's a sender, there's a receiver, the sender is sending traffic, and the receiver says, you know what, I'm getting overwhelmed, my buffers are getting full, you need to slow down, otherwise I would have to drop the packets. So the way it informs the sender, the way receiver informs the sender by using a priority-based flow control, it uses pause frames for that. This function must be configured on all the switches consistently, all the network ports consistently. You can do that manually, or you just use the built-in templates of Nexus Dashboard or HyperFabric for AI. This is so built in that when you configure the fabric, the AI type fabric in Nexus Dashboard, you won't even see the option, hey, where do I enable it? You would have to go actually a bit deep down. It's that simplified. It goes and configures everything consistently across the network. So that's a big, big benefit of using these products. The other quick point I'll mention, that's not just about the packet loss, not just about packet drop. Even if there's a network delay, where the packets are not dropped, but the packets are delayed. For example, let's say there's a packet that's trying to go out of a switch port, but the packet is stuck in a queue with 100 other packets ahead of that packet. Even then, the performance would be significantly delayed or degraded because of the same reason. As I said, the tail latency will increase. Here, there's no packet loss. Right? So the ideas are the same. So packet loss or network delay all means significant performance degradation. We want to avoid all that. Now, what are the other reasons of network delays? Right? This is something we have been seeing forever, right? It takes a while for a bit to transfer or travel on the wire. It takes a while to transmit a packet on the link, depending on how fast the link is running, and so on. Can we change that? No. As an operator, if your network is already operational, you cannot change that. You cannot just magically increase the speed of a link after the link is operational. But what you can do, you can design your networks in a better way that minimizes the network delay. And for that, there are some designs that are very specific for AI clusters. So we'll talk about that next. When we talk about these AI cluster backend network designs, there are two newer concepts here that have not been seen before. Number one, we design these networks in a non-blocking way. Most of the times, of course, there are some exceptions to this rule, but most of the times, what do I mean by non-blocking? Essentially, if you take the example of a 64-port switch, we take half of those ports, 32, we connect to the GPU NICs, and then rest 32 ports go connect to the spines. So that means if there's 800 gig of traffic is coming to the switch, there must be 800 gig of capacity to send out this traffic on the switch. Right, and by the way, these are the switch models that you see on the screen. The one on the left is a Cisco Silicon One based switch. The one on the right has the ASIC from NVIDIA. Do they look any different? No, they don't look any different. Both of them have 64 cages capable of sending and receiving traffic at 800 gig. And using the example of these switches, I made that diagram. So if you create this diagram on every switch, if you have 32 downlinks, and if you have 8 of these switches, you can connect all the way up to 256 GPUs, 8 multiplied by 32. And assuming there are 8 GPUs within a node, we are talking about around 32 servers. Why do we do non-blocking? As I said, all these GPUs send and receive traffic at line rate. So there must be enough capacity in the network to provide the performance that they need. So that's one. The other is the concept of rails. And this is a very specific pattern. So there are 2 points that I'm saying here. Number one, we connect them in a specific way, and then there's a benefit. So let's talk about them. That why exactly we connect, like the first NIC to the first leaf, the second NIC to the second leaf, and so on. And then the rail optimization, what it does, it of course reduces the network delay. It also reduces or maybe eliminates the traffic that goes to the spines. Now to understand that, we're going to go back to the little bit basics. Right? What exactly is happening with, between the GPUs and how exactly they're talking? So remember, when GPUs talk, there's a whole idea of collective communication. That means all of them are talking together. There are some software libraries for it. Every vendor has their own software libraries for it. Like NVIDIA has NVIDIA's collective communication library. We call it as NCCL. Then AMD has its own collective communication library. It's called RCOM Collective Communication Library, as in RICL. And then Intel acquired this company called Habana, and they had HICL. That's all you need to know. You have the drawings of how exactly these communication patterns work. Trust me, if you're focusing on network, and this is where this session is focusing, you can read more about that, but all you need to do, UDP IP packets on the network, right? Question?
Yes, so when you say all the GPUs, they are talking, if you have a cluster with, let's say, 10,000 of them, do you mean all of them are talking at the same time?
Yes, even if,
You send a message from one, it has to be
yes,
10,000?
yes. Depends on the job, depends on the scenarios. If you have a job that's large enough that runs on all these GPUs, then yes, all these GPUs are talking to each other, and I'm going to explain that a bit more, right? So here is a very, very simple example. Right now, we're talking about training a large language model. Essentially, it boils down to mathematical calculations. So I have a very simple example here. Let's say there are 40 numbers to add. In reality, there might be 4 billion or 40 billion. But let's simplify this whole challenge and make it 40 numbers. And there are 4 GPUs. So to speed up this whole calculation, what I can do, instead of adding all these 40 numbers on one GPU, I can say that first set of 10 numbers, GPU 1 will do the sum. The second set will be handled by GPU 2, the third set will be handled by GPU 3, and fourth set will be added by GPU 4, right? So now I've done the distribution of this problem. This is the basics of distributed computing. And by the way, these are not just numbers, these are big, big matrices, tensors. If you've heard of that term, tensor, it's a multi-dimensional array. So all that mathematics is going on behind that. I've oversimplified this problem, okay? After the data has been distributed, let's say these GPUs add this number. So now there's one value remain. Everybody added those 10 numbers, there's one value remain. At this point, all these GPUs have their state of their own. So GPU 1 doesn't know what's the sum of GPU 2, right? Or what the sum that GPU 2 got. So they must sync their state. So one of the ways of syncing the state is very, very easy, which is totally inefficient, but this is the easiest one, where GPU2, GPU3, and GPU4 sends their data to GPU1, and then GPU1 adds 1, 2, 3, 4 again and sends the same information to everybody else. Now imagine to a 10,000 GPU example, if you try to do this with 10,000 GPUs, super inefficient, because now you caused an in-cast problem GPU1. GPU1 is struggling, while what are the rest of the GPUs doing? Nothing. They're sitting idle. So we don't want to do that, right? This is the simplest way, but nobody uses this kind of approach. The other approach could be GPU1 sends its information to GPU2. Exactly at the same time, GPU2 sends its information to GPU3. Exactly at the same time, GPU3 sends its information to GPU4, and GPU4 sends its information to GPU1. So this is first sync. So when you talk about 10,000 GPUs syncing, expand this whole idea to 10,000 GPUs, and this is how they're syncing their information. And then these GPUs repeat this cycle again, and then they repeat it again. So if there are 4 GPUs, if you repeat this transfer of data 3 times, or if you have n GPUs, you repeat this cycle of information exchange n minus 1 times, all the GPUs will learn the state of all other GPUs in the cluster. The benefit of this approach is no GPU sitting idle, and we did not cause a specific bottleneck in the network. All the network is synchronous. Making sense till now? Oversimplified it, yes, but hopefully it conveys the point. But remember, there are not just 4 GPUs here. I said that there are standardized servers out there, very well used. These servers have 8 GPUs within them. Right? So if these 8 GPUs are synchronized their data, they create a ring, just like you saw before. So they create a ring. And if there's another server, that also creates a ring. So if you have one job that needs 8 GPUs, fine. Server 1 is doing its own thing, server 2 is doing their own thing. But now if you have a job that needs 16 GPUs, then these servers must talk. Only then they can sync their data. So server 1 creates its ring, server 2 creates its ring, and the ring must connect. So this is how it connects. It connects on the same GPU ID. And the same thing is repeated by other GPUs. So GPU2 will create a ring on both the nodes, and that also must connect. Only then the synchronization of data may happen. And then we repeat it for all the GPUs. Now, if this challenge is brought to you, and if you're a network engineer, it's like, how should I connect these servers? It's like, connect them via the same switch. So essentially, NIC 1 should go to the same switch. That's exactly what we do in Rail Optimized Design. And this is the basic reason why Rail Optimized Design was invented. It provides single hop forwarding between all the GPUs of the server. In this state, traffic is not even going to the spines. That brings to the next question. So when is traffic going to the spines, by the way? Why do I have spines here? So I have some examples here to clarify it. So let's say if there's a job that needs 8 GPUs, another job that needs 8 GPUs. So traffic within the servers only goes through the internal communication channels of the server. So if it's NVIDIA, they use NV switches. So let's say in this example, GPU1 goes to NV switch and then goes to GPU2. But let's say now there's a job that needs 16 GPUs. What would happen? GPU1 will go to NIC 1, NIC 1 to leaf 1 down to NIC 1 of node 2, and then goes to the first GPU of second node. And the next common question that comes is, hey, does the first GPU never talk to second GPU? Oh, it does. But the way it talks is like from GPU1, it goes to the NV switch and goes to GPU2, and then goes out to leaf 2, and then comes down, as you see here in the drawing. Why? Because it's always assumed, that's the right thing, that the internal communication path of the switch or the server is faster than the network path connectivity. Okay? Now there is a question.
What's
you're asking what's the protocol here?
Yes.
It's Rocky.
Rocky.
Yes, when the GPUs talk over the network, it's RDMA over converged Ethernet. So these are UDP IP packets. Remember a few slides earlier had this whole Rocky packet sequence number shown with first, middle, last going on. That's how it works.
Rocky is a transport, but in terms of building out an idea of the network where the GPUs live.
So much before, so the question is how exactly the GPUs discover each other and how do they decide when to talk, how to talk. Much before the traffic really starts, the collective communication library, NCCL in this case, discovers all these GPUs. And it says that, all right, GPU 1 and GPU 2 connects via NV switch. Fine, great. Now, GPU 1 of first server and GPU 2 of second server, they connect via the leaf 1, right? So that whole discovery happens much before the real RDMA data transfer happens.
Yeah. So is that based on BGP or what's the underlying?
That's not a network routing protocol. The discovery of GPU is not a network routing protocol, right? So I can explain a bit more on detail. That's a fairly detailed topic, right?
Yeah.
Right. Now, what are the conditions when traffic goes to the spine? Number one, let's say link failure. If let's say the NIC 1 fails, then this is how your traffic communication would look like. From GPU 1, the traffic will take the NV switch path, will go to GPU 2, then it will go to leaf 2. Via the spines, it will go to leaf 1 and come back on the GPU 1 of the second node. So this is why you need spines. This is one of the reasons you need spines. The other reason is maybe you are a research or academia field. You're not using NCCL. You're using some other collective communication library that may not be optimized for all these enhancements. That's another reason traffic goes to the spines. There are some servers in the market that don't have NV switches, just for some cost savings. If you do that, then the traffic is going to the network. Or maybe are you using a NCCL version that's not optimized for all these scenarios? These are some of the reasons. However, the biggest reason why traffic goes to the spines when you have a lot more servers, a lot more GPUs. So let's say if you have a scalable unit of 256 GPUs, another scalable unit of 256 GPUs, and you are running a job that requires 500 GPUs, traffic has to go to the spines. That's the only way they can talk, right? Because there's only so many links you can connect to a single switch. Question?
So, say these are the spine leaves are in different locations, maybe on different sides of the data center. You're saying Rocky is what is doing all the routing essentially?
The fabric is doing all the routing, right? Essentially, I have that covered a few minutes later, but all you need to do is like all these NICs that you see, on Linux, they show up as Linux interfaces. They have IP addresses on them. Then all the switch ports. Layer 3. Most of the time it's layer 3. Then all the switch ports, we convert them into layer 3. You could also run layer 2, but we convert them into layer 3, assigning IP addresses to them. Then we use one of the routing protocols, BGP or whatever you like to use, just provide connectivity to them. Right? It's as simple as that. Configuring these environments is probably a relatively easier task, honestly. And compared to the other kind of networks that we run around our data centers or even the internet, configuring is a relatively easier task here. Understanding these details, like why exactly traffic is not going or what exactly it's going, is a newer concepts here, right? But remember, these are Linux interfaces. They have IP addresses on them. If you want to allow the communication, how would you do it? Going back to the basics. That's what is happening here. Question?
In terms of when you scale out for more than 32 nodes and you get two sets of, let's say, fabrics, and there's spine-to-spine communication, is there any testing done in terms of what is the performance degradation, if any, when you scale within 32 nodes versus when you go between two 32 nodes, because of not scale versus spine by spine?
Well, it depends on many, many factors. There's no single answer. Of course, there's a performance degradation, and this is the whole reason I'm going to the basics and bringing the whole concept of network delay. So imagine if the traffic goes to the spine and the switch causes 1 microsecond of latency, now you're causing 3 microseconds of latency. So of course, there would be performance degradation. How much? Depends. What job it is, what collective it's running, and many other factors.
And then for the same reason, I would imagine all of this needs to be in the same physical
It should be.
Can't really go into a data center, those things.
I mean, people do that, but make the cable length as short as possible, right? Look, the entire reason of RDMA was implemented because people wanted to save those microseconds of delay that's caused by TCP. And if I'm spending the time in a longer cable, my whole, basic reasoning is gone. I should not do that. So if I have, in my lab, I had 30 meters cable, and then I had 50 meter cables, and I had 10 meter cables. I use 10 meter cables everywhere where I can. Then I stick with 30. I keep all the cables consistent, because if one cable is 100 meter, another one is 30 meter, now it's going to cause problem. That's why this whole idea of hyperfabric for AI is so important, because everything is consistently delivered. All these factors play a major role, and performance may go off the window if there's some inconsistency in the network. Okay, now there is some evolution happening with the backend network designs. So today, the design that I showed you before is typically called as a single plane design. The way we do it, if we have the server like this, as you can see, we put a transceiver on it. It has 2 ports. We use 2 cables and connect to the transceiver. I think the other day somebody was asking questions, so I added this picture here. And this is a 800 gig connection between 1 NIC and 1 switch port. What we are seeing now as an evolution is a multi-plane design. What we do is we take 1 cable to 1 switch and another cable to another switch. And instead of sending 800 gig of traffic to the same switch port, we send 400 gig traffic on 1 port of 1 switch and 400 gig of traffic on a different port on a different switch. Why do we do that? There are a few reasons. Number 1 reason, or 2 reasons you're going to see here. So this is the backend network design we are looking at. 256 GPUs connected within a scalable unit, all benefiting from the single hop forwarding via the leaf switches. Traffic is not going to the spines. If you have to create a cluster of 5 and 12 GPUs, one of the ways you can do something like this. We already looked at this, right? But now if you have a job that needs 5 and 12 GPUs, traffic is going to the spines. The other way is I can create a multi-plane design. And instead of connecting an entire 800 gig capacity from a NIC to the same switch port, I send 400 gig on first plane and another 400 on second plane. Now the GPUs are benefiting from the single hop forwarding, because the switch can connect more endpoints, because the switch is not connecting at 800 gig anymore. It's connecting at 400 gig now. And because of that, the number of interfaces are double, right? So 64 800 gig ports are treated as 128 of 400 gig ports, right? We call it as a radix of switch, if that's another term that you like to hear, right? Also, the other benefit is if one of the plane fails, let's say one of the link or one of the leaf switch fails, the other plane is still there. Of course, the performance will get degraded, but at least the network is there. So your jobs will at least run. So that's the other benefit. Right? So this is a kind of evolution. Do you really need dual plane design all the time? No. But if you want those benefits of a single hop forwarding, and especially you're designing larger clusters, then yes, multi-plane design has some merits there. Question?
Are your customers complaining that 800 gig is not fast enough, or that tend to be okay?
Say that question again.
800 gig is a lot, right? But your customers, is that enough for them, or would they complain and they say they want faster speeds?
800 gig links are fully saturated in these environments. So if you are running an environment where your network is fully saturated, and if your management is asking, hey, what's your budget requirement for next year? What is that you're going to ask me? Or any vendor you're buying from, you're going to say, hey, double my network speed, right? That's how it works. So that's your answer. All the links are fully saturated in these cases. These GPUs send and receive traffic at line rate. That's the basic premise, and that's why this whole AI networking has become such a critical field.
So, if the networks, the links are saturated, and then you're dividing the 800 by 2 to go to leaf 2, what's the implications of that then?
What the implications of that?
Yeah. So
Of a dual plane design?
Yes.
Well, that's a long answer. There are some benefits I gave you. So there are two implications that you clearly see, which is high availability and single hop forwarding. So it has some benefits out of it, right? The inventory, the number of switches, the number of cables, the number of transceivers remain the same, whether it's like the design on the top or the design on the bottom. So that's not changing. Your cost is not increasing, right? We can talk more if seems like there's more to a question. There's something more you're expecting, but we can talk more.
What is usually the latency between these when you connect these systems or GPUs? What is the latency we're talking here in nanoseconds? How you measure that?
So typically, look, a switch would have a latency of less than a microsecond, like maybe 800 nanoseconds, like of that order. There's a standard test, which is like IB latency test. If you run that, the output of that would be around 3 to 4 microseconds. So that's what your application is seeing, imagine. 3-4 microseconds of latency. That includes your stack delay, your NIC delay, your switching delay, everything else. Right? There are also some tests that we have run in special scenarios that hits around 1 to 2 microseconds of delay. So that's what we are talking about. But remember, any delay that we talk about adds up. Remember I showed that 4GP example of collective going in circle? So if you add even few nanoseconds at one link, and then you have to add it 10,000 times if you have 10,000 GPUs. So that's the reason every delay factor is so important.
How much it is comparable to InfiniBand?
It is comparable.
You're achieving the same latency?
Yeah. So the question is comparing to InfiniBand. We have published bunch of benchmarks that all the results are comparable to what the InfiniBand-based networks are providing. And not just our own results. If you look across the industry, most of the hyperscalers are building Ethernet-based, RoCE-based clusters because of the same reason, because the performance is comparable. Right? If you go by the data sheets, the number differ. And that's why we have to run benchmarks. Right? Because if you just make buying decisions on data sheets, then good luck. Okay, but yeah, the performance is comparable, and I can share more information later. Okay, let's talk about network congestion, because that's our favorite topic. And this is a significant challenge in RoCE-based, Ethernet-based networks. Why? Because traditionally, Ethernet-based networks do load balancing based on 5 tuples in the packet header, which is UDP and the UDP source port and the UDP destination port and the source IP address and the destination IP address. The selection of one of the links from the equal cost links is random. And that selection algorithm does not account for the real-time usage of the link. So when you do things randomly without even knowing what's happening right now, it's possible that both the flows, when spine one sends, end up taking the same link. And this is not just theory. This is quite evident. Like anybody who has run this environment, happens quite a lot. And this is one of the examples. I have the output of a graph that you see on top left. I'm sure if you're running environments, you're running networks, this is the kind of problem you see almost everywhere. It just doesn't become evident. You know why? Because let's say if you have 2 links, one link runs at 40%, the other link runs at 60%. Is that a problem? No. I mean, you can live with that. Like, for sure, you would love to have 50-50, but 60-40 is okay. The problem is you need the 100% capacity out of this network when your end devices are sending and receiving traffic at 800 gig capacity. You already designed your network to 1:1 over subscription ratio. So one link is trying to run at 100% and trying to send more traffic on it, while the other link is sitting idle at 80%. Not okay. Now you're wasting the investment there, and you will run into congestion. Right? So that's where the problem becomes more critical. That you're already pushing your network to the full capacity while some of the links are sitting idle, so you want those idle links to operate. So we want to solve this problem. And one of the ways to solve this problem is called dynamic load balancing. Dynamic load balancing is a feature on our Cisco switches. It has multiple modes. One of them is a flowlet mode. The way flowlet works, that it uses the same layer 4 flow, the 5-tuple flow, and then it looks for inter-packet gap. And if the inter-packet gap is longer than a configured threshold, the next set of packets are identified as a new flowlet. And then the switch looks at the real-time usage of the links and the real-time congestion states of the link and sends this next flowlet on the least congested and least available or the least used links in real time. So you see the graph on the left, and compared to the graph on the right, the links become nearly uniform. Not perfectly uniform, but nearly uniform. So that's one approach. The other one is, we don't do this using flowlets, because remember, the flowlets only achieve a nearer uniform utilization of the links, because each flowlet may be of different size. So what we do, we take one packet sent on first link, we take second packet on second link, third packet on third link, and so on. It's called packet spray. By the way, it's not that easy the way I described it, because it accounts for the real-time congestion states of each link. If third link is congested for a second, or maybe there's another packet that's being transmitted to a third link, the whole algorithm skips that link and goes to the next equal cost link in the whole group. And because of that, the utilization of all these equal cost links is totally uniform, as you can see with the graph on the right. But I think the other day we were talking about, somebody asked a question that, hey, wouldn't this cause an out of order arrival of the packets on the receiver? Because something that has been a big no-no in the networking industry, because the NICs have to hold the burden of handling that out-of-order arrival of the packets. So this is, again, another major pillar of Cisco's and NVIDIA's partnership with Spectrum-X has a role to play. And to explain that, I have a very simple example. Now imagine there are two nodes. And node 1 is trying to do a RDMA transfer of the data from the GPU memory to another GPU memory. And imagine the data size is so that it can fit in 4 packets. So we have first super NIC on first NIC, or the sender node. It sends those packets. The sender sends the packets in order. No problem there. But when leaf 1 sends those packets, it's possible. I'm not saying it must, but it may cause a bit reordering of the packets. Maybe it sends first packet, and then it sends second packet, but the second packet is slightly delayed, and the third packet goes earlier. And the same sequence repeats on the spines too, because now there are 2 spines. So these 2 spines are like, acting by themselves, and even different links are acting by themselves up to an extent if these links are slightly congested for a second. And the 4 packets do arrive on the receiving leaf, which is leaf 2. And when the leaf 2 sends these 4 packets to the receiving super NIC, it receives them out of order. And this is where the Spectrum-X integration happens, which is a feature called adaptive routing, or there's a feature called direct data placement. So the super NIC looks at every packet and places the payload of every packet in the correct memory location. Right? So this is how we handle the out-of-order arrival of the packets while achieving the uniform utilization of the network. So the networks are almost like, we can hit like up to 95% utilization of the networks. Question?
Does that work also on the MGXs where there's a 2-1 subscription of the NIC?
Yes. This feature will work on MGX servers as well. Right? So the question was about a specific, not the EdgeGX architecture, but MGX. This feature is available between Cisco switches running NXOS 10.6.1 release, when you have NVIDIA's Bluefield 3 Super NICs or ConnectX 8 NICs as well. That's all we need. So it will work on the MGX servers as well. So what's the benefit? This is one experimentation that I did. There are many other experiments showing a lot more value. So you see the graph on the left. It shows the output of an all-to-all collective output between 64 GPUs, and it shows the value of around 36 gigabytes per second. When we enable packet spray on Cisco switches working together with Spectrum-X on NVIDIA SuperNICs, the performance goes to around 50 gigabytes per second. That's around 35 to 40% improvement. That's a major, major improvement. When people are spending so much in such an expensive infrastructure, this is a major, major improvement. Now, can this problem happen only on the backend networks between GPUs to GPUs? Remember, I mentioned a few minutes earlier, this problem happens everywhere. It just doesn't bother you today because it's 60-40. But if it becomes 100-80, it bothers you then. Well, we started seeing this problem on the front-end networks too. Why? Because we merged the front-end network and the storage networks. If there's high-performance storage and you're reading data from storage, the storage is sending traffic at line rate. So the same problem happened there too. But the other challenge of the front-end network too, we are sharing. Remember a few minutes earlier, I showed that slide. There's TCP, there's RoCE, there's like NFS over TCP, all kind of traffic coexist. So we cannot just like load balance or packet spray all the traffic. So we came up with this feature called policy-driven load balancing. And we said that all the RoCE traffic that needs that high performance and is connected to SuperNICs, we do packet spray. Other storage traffic may benefit from flowlet dynamic load balancing, and rest of the TCP traffic, your file transfer, your FTP, your HTTP, go to the default value. We don't want to touch it. Because if we touch it, we need those the handling of out-of-order arrival on the receiver. We don't want to touch every device. We just want preferential treatment of different traffic type based on the traffic type. So this feature is available, I think, for a few months now, or on Nexus 9000 switches.
You said there was a requirement for the NIC and the switch to communicate to support. What role does the switch play in that? Because the NIC seems to be the one doing all the heavy lifting.
So the switches are spraying the traffic. And it's not just a dumb spray, as I said. It's a very careful and intelligent spray because it must account for the congestion states of the link. So that's number one. And also, the whole solution must be validated, right? Remember, that's the first point that I mentioned in the beginning, that we just give you something that is not validated, that, hey, you can use this NIC and that thing, which is not standardized, it would work. Maybe it works, maybe it does not.
So is it bidirectional coming in that when it comes from the model going out to the switch, it's always pinned to the one link, but it's only from the switch in the spray? Which direction does
The spray happens in, any traffic that's going out of a link, it's capable to spray that, right? But the point that I'm trying to say is that it has to do a lot with the validation too, right? So we can't just like randomly enable anywhere just because the capability exists, but the whole validation piece has to play a role too here, right? All right, let's quickly talk about how do we configure the networks. Look, configuration is really simple. That's why I only have one slide on it. And we have written many papers. All these GPU NICs show up as interfaces on Linux. Most of the time, people use Linux for it, right? We configure IP addresses on them. Typically, we put them in /30 or /31. Then wherever these links connect to on switch ports, we assign matching IP address, whatever the IP address might be in /30 and /31 subnets. Then we run a routing protocol in the network. You can use any routing protocol that you like. We recommend eBGP because there are some specific features in eBGP for that. And just maybe redistribute the route, or maybe there might be 4 other ways. You might have some preferences of how do you make the communication work between the subnets. That's number one. Number two, you increase the MTUs on your Linux interfaces to 4K. That's typically the RoCE MTU size. And then you also adjust the MTUs on your network. Make sure you account for the packet header overhead. So increase it to 4200. Or if you just want to keep it simple, that's what I do. Just increase it to 9216. Just remove all these issues. Consistently go increase all the MTUs on the network. You also got to enable priority-based flow control. across the network on all interfaces. Then you use some of the congestion control algorithms. And if you're using something called as a data center quantized congestion notification, you enable marking of the ECN bits in the IP header. And when you do that, the receiver of that ECN mark bit may send some special congestion notification packet, CNP. So you want to make your network configure to send that CNP packet with priority. So you assign that CNP packet in a priority queue. That would be QoS configuration. And then if you need DLB, dynamic load balancing, you enable that. Like features like Spectrum X, you enable that. Features like adaptive routing, you enable that. And then you need the observability, like the visibility piece to it. Now, all these steps you can do as CLI, but please don't do that, trust me. Use some kind of automation platform for that, like Nexus Dashboard. As I said, like all these steps look quite complex. They're probably like hundreds of lines of configs, all simplified by Nexus Dashboard with few templates. Question?
As we know, again, just stepping back for a second. So in the front-end networks, as we know it, we know that within Cisco world there is DCNM-based, integrated spanning leaf architectures or Cisco ACI-based integrated spanning leaf architectures. When you come back into the back-end network, which is again a spanning leaf, do you consider any of those, or is there another Cisco validated designs that you must follow, or in ideal world to make sure you know what you're doing?
Yeah, so the question is what network design we use on backend. It's typically spine and leaf. You saw some of my drawings, leaf, standard leaves, spines, with differences. You remember two major differences I talked about, non-blocking and rail optimized. Otherwise, it's spine and leaf, yeah.
And obviously you wouldn't go ACI on that, I'm guessing.
You may go, yeah. I mean, look, most of the features you see today we have prioritized on NXOS. The reason is this field is evolving so fast.
Has any of your clients on the back end as ACI?
Yes, there are a few, yeah. Very special scenario. If you ask me, I recommend to go with NXOS for the reason I said. This field is evolving very fast. We have features that we are only delivering on NXOS. Probably we will do that on ACI. But if you want to get the latest and the greatest, stick with NXOS. Like I talk about priority-based, DLB, that's only on NXOS. There are some other features only on NXOS. This whole automation that I'm talking about on the slide on Nexus Dashboard, that's only for NXOS, right? If I have unlimited resources, I can do that everywhere. But, we have to prioritize our resources. Let me complete the last few slides, and then we can continue talking, yeah? So the next piece is observability. Look, you will find some list of the metrics that I found relevant doing all this benchmarking work, validation work by doing AI cluster buildup in Cisco. Every metric that you see on the slide has a story behind it, right? This is not an exhaustive list, by the way. If you think you need more metrics here, yes, you need more metrics here, of course. More the merrier. This is the minimum required list that you should not go to production without these metrics coming to some kind of tool. You can have your own tools going on, by the way. We are totally okay with that. You see some of the examples here, right? These examples are coming from some of the tools that I have built. Like here, this is an example where I lost a GPU. In a 248 GPU cluster, I lost one GPU. Of course, my job will not run because the GPU is not there. I have another output where my job did not start, and I had no freaking idea why the job did not work. I tried for 3 days. And then I looked at this heat map. It shows me the power utilization of the GPUs. And one of the GPUs shows 320%. It's like, how can the power utilization go to 320%? That's not even a thing. If the GPU is clocked at 800 watts, it can take 800 watts. It cannot go to 1900 watts. I replaced the GPU and things started working. My guess is probably the GPU melted. That's why it's sensor. No, this is real. Honestly, these GPUs literally melt. I have seen those scenarios. There are similar graphs that I don't have on the slide where the training is running, a job is running, and then the temperature graph is going up, and the training crashed. I go back to my tool and look, there's no reporting after that. The graph is like blank after that. That tells me the GPU melted. It's not telling me anymore what's its temperature. I replace the GPU and things work. So this is one example like that. Trust me, if you don't have these tools, it's extremely complex to proceed and go to that success of the investment that you're making. This is another tool that I built. It's available on GitHub. It gathers all the Rocky relevant metrics from Nexus 9000 switches and puts in a use case focused panels. One of the examples that you see towards bottom right, which is correlating pause frames with ECN marked packet and comparing percentage, like what's the percentage of traffic that's getting ECN marked? That gives you congestion severity. You can use all that for free today, but what we're doing, we're bringing all these use cases. We took the learnings from all the pitfalls that we ran into, and we're bringing them into Nexus Dashboard. So this is one screenshot. It's not available today. We're planning for this to be shipped in Nexus Dashboard 4.2 release, which is still a few months away. And not just the metrics of the network, we are also bringing metrics of GPUs, the NICs, and also the job scheduler. There's a commonly used scheduler out there. It's called Slurm. I think somebody was asking about the other day. So this is one view that you see that it tells you the network path taken by a distributed job, and if there's anything that goes wrong in that network path, it will generate an anomaly. This kind of correlation will save you days. Trust me. Ask me how many days I've spent in this kind of correlation when some hot temperature causing bit errors, causing packet drops, and that's degrading the performance. You can reduce that troubleshooting cycle from days to hours, if not minutes. Okay, a quick word on Ultra Ethernet. If you have any questions, you can stay back and we can talk about it. But this is a lot of companies came together and they try to enhance Ethernet for high performance computing and large AI cluster demands. The good thing is most of the features that they talk about, most of the things that they have mentioned in their specification, the mandatory features are already there. Anything optional, because of the programmable architecture of our Silicon One NPU, we will deliver when the ecosystem is ready, because we don't just want to deliver a feature and it's like, okay, what do I do with it? Right? Because most of these features work end to end. Now, somebody was asking a question, okay, why NIC plus switch handshake? Because a lot of these things work together. Things don't just work by one component being ready. This is a summary of the commitments that we made about the partnership of NVIDIA and Cisco. If you think about last 90 minutes, I explained all of them in detail. The first one is about the reference architectures. The second one is about the switch, which has the NVIDIA's Ethernet silicon with the Cisco Nexus NXOS or Silicon One based or Sonic operating system managed by Nexus Dashboard. And the third one is about the adaptive routing feature, and that also we talked about how exactly packet spray work with NVIDIA SuperNICs. Right, so the final point that I want to say is that I know the title of this session was why Nexus 9000 switches for AI networking. That's super marketing, right? I like to summarize it to 3 bullets. If you're building AI networking, think about the entire system, not just about switches or one feature here and there. In Cisco, I did not even talk about transceivers today. I think yesterday we were talking to some of you without really telling who I was talking to. Some of you have concerns about transceiver being failed quite fast. In Cisco, we have the entire transceiver group, being many companies being acquired, and our failure rate are significantly lower from the industry standards. And then the switches, then the silicon, not just Cisco's own Silicon One, NVIDIA Silicon 2, fully packaged in our own switches and managed by the own operating systems. So that's number one. Number two, the common operating model. If you want to use on-premises, you can use Nexus Dashboard. If you want to use cloud control, you can use HyperFabric. And the third one is to make you feel confident. We have all these industry validations, including the GPU benchmarking team, so that you can deploy confidently. Right? So the idea is that regardless whether hyperscaler or neoclouds or enterprises, or which GPU vendor or what NIC or which storage vendor, we want to provide a consistent Cisco networking experience. Okay, so with that, I'd like to thank you for your time. That's all I have for today, but I'm here if you have any more questions. And one final request, please take your surveys, because I think our SGMs give us hard time if you guys don't fill up survey. So please take up surveys and enjoy the rest of your show. Yeah.